Alright, what's up? Time for the rest of section 4.7 right now. We just got done looking at some more difficult exponential equations than what we had seen previously in the chapter. And now what we're going to do is we're going to be solving some more logarithmic equations that are a bit more complex than what we've seen before as well. Alright, these aren't quite as difficult as those exponential equations. So if you got those down, you got the hard stuff down. But nevertheless, some things you're going to have to pay attention to here. I'd like to talk about two different methods for solving logarithmic equations. We're going to get back to the point where we're solving logarithmic equations by exponentiating both sides of the equation. But before that, I want to show you another method that's pretty useful in many instances, and that's the equating arguments method. Alright, now I need to make a quick note here because what your textbook calls an argument I have referred to differently in class. The argument of a logarithm is what we've been referring to as the index. Okay, so equating the indexes method, or indices method, if you want to use a more correct term actually. Now the idea is this, and it's a really simple one. If you have two logarithms that are equal to one another, alright, I've got a log base 3 of something equals a log base 3 of something. In order for that equation to be true, the indexes or the arguments have to be equal to each other as well. Alright, so it would be true in this case that 4x minus 1 is equal to 7x plus 5. How else would these two base 3 logarithms be equal to one another? So we can just go ahead and set those equal. 4x minus 1 is equal to 7x plus 5. So we get negative 3x is equal to 6 and x is equal to negative 2. Pretty simple, right? One more thing that I need to emphasize here with logarithmic equations that you didn't have to think about with exponential equations. And that is this. With logarithmic equations, you have to check your answers, you check your solutions, because you have to make sure that the value of x that you got is actually part of the domain of the logarithms that it was a solution for. Remember, you cannot take a logarithm of a negative number or of 0. So if I plug in the answer that I got, negative 2, into either argument, and I get a negative value, or a non-positive value I should say, then that means this was actually not a solution at all. Alright, now, if I plug in negative 2 for 4x minus 1, that's going to give me negative 8 minus 1, that's going to give me negative 9. And I cannot take a logarithm of negative 9. So, that means, since this solution would give me an undefined logarithm, that it's not actually a solution at all. And since we didn't have any other solutions, that means there are no solutions to this particular logarithmic equation. Sometimes you can't find a value of x that would make two logarithms equal to one another. Alright? And by the way, when you get an answer that doesn't actually work when you plug it back into the equation, that's something that you ought to know is an extraneous solution, and that's exactly what negative 2 was here, was extraneous. Alright, but the equating arguments method was pretty simple to use, right? Well, next example. Now you're going to see more logarithms in this example. In order to use the equating arguments method, you have to have exactly one logarithm on the left side of the equation that's equal to exactly one logarithm on the right side of the equation. So, how in the world are we going to handle this where we've got two logarithms on the same side? How about using some of those properties that we learned in order to combine these two logarithms into a single logarithm? The product property looks like it would work pretty well to me here. Let's go ahead and use it then. So for the log base 5 of x plus log base 5 of x minus 1, we can make that then log base 5 of x squared minus x. Right? If you multiply x times x minus 1, you get x squared minus x. Alright, we'll have that equal to 2x plus 3 on the right side of the equation. And now, the two indexes or the two arguments are equal to one another because we have two logarithms with the same base that are equal to one another. So we'll set x squared minus x equal to 2x plus 3 and solve. Now remember, with quadratic equations you set the equation equal to 0 in order to solve. So we're going to get x squared minus 3x minus 3 equals 0. And if it's an easiest problem as it could be, this would be a factorable expression. Turns out not to be factorable, so we're going to use quadratic formula really quickly here. I'll just go ahead and plug in the numbers into the formula. You can do the same, you don't have to wait on me. Alright, now I've done a little bit of the work mentally, but there's my opposite of b. There's my b squared. There's my minus 4ac right there. So we end up with these two solutions. 3 plus the square root of 21 divided by 2, and 3 minus the square root of 21 divided by 2. Now remember, we want to make sure that neither of those would make us take a logarithm of a negative number. A little bit tougher in this form. Hopefully this is a calculator question if you get one that doesn't give you integer values. So you can check this out a little bit. I'm going to go ahead and show you what the decimal values for each of these things are. Let's round them to 3 significant figures. And that'll give us 3.79 for one of them. It'll give us negative 0.791 for the other. Alright, and let's think about whether either of those would give us a negative value. Alright, if I plug in positive 3.79 into 2x plus 3, hopefully it's fairly obvious that that will give us a positive value, right? For x squared minus x, if we just estimate that as being about 4, you would have about 16 minus 4, so that's definitely going to be a positive value as well. Now let's think about the negative 0.791. Let's just pretend that was negative 1. If that was negative 1, you'd have negative 2 plus 3, and that would still be positive, isn't it? Okay, so this is still going to give you a positive value when you plug it in. And again, let's go with the negative 1 thing. If we had negative 1 squared minus negative 1, that would be the same as 1 plus 1. Both of these answers will give you positive values to take logarithms of, so they're both solutions. There we go. One more for you to try with the equating arguments method. Go for it. Alright, remember the first goal was let's make sure we only have one logarithm on either side, so use the quotient property in this case. Then equate the arguments. Alright, now once we get here, we're going to have to get rid of this x in the denominator by multiplying both sides by x. Remember to distribute when you do that on the right side. It would just cancel out the denominator on the left. In fact, let me show a little extra work with this one. See how when you multiply the left side by x, the denominator cancels, leaves you with x plus 1. And on the right side, you distribute and you get x squared plus 3x. Okay, well again, let's set this quadratic equation that we've got equal to 0. And I'll bring everything to the right side so that the x squared can be positive. That'll give us x squared plus 2x minus 1. Now again, this is one that happens not to be factorable, so you can use quadratic formula real nice and easily here. Alright, you ought to be able to get to that part to verify what I've got there, and so we have negative 2 plus the square root of 8 divided by 2 for one solution, and for the other solution, of course, it's going to be negative 2 minus the square root of 8 plus, over 2. And just to make it easier to check again, let's change those each to decimals. And then we'll want to go ahead and plug those values in as well as we can mentally. Alright, if we plug in positive 0.414, well, that plus 1 is still going to be positive, isn't it? And it is already positive, so it's good in that logarithm. And a positive number plus 3 is still positive. So this value will work in all three logarithms, no problem. Negative 2.41, however, would only work in this one. Yeah, right? That was about negative 2.5. Negative 2.5 plus 3 is positive. But it would make this a logarithm of a negative number. It would also make this a logarithm of a negative number. So we only had one solution here. So I'll highlight that and I'll label the other one as extraneous. That's the equating arguments method. Now the other method is the one that we've already used before, this exponential method. And the idea with the exponential method is that you're going to use exponents to get rid of logarithms because they are inverses of one another. And we can do exactly the way we've done before, where we're going to raise both sides to the power of whatever the base of the logarithm is on one side of the equation. So we're going to make both sides, when we exponentiate, a power of 11 here. And as we want, the 11 and the log base 11 are going to cancel, leave you with 5x minus 4. We'll have 11 squared there, which will give us 121. And then we got a two-step process. And we find out that x is equal to 25. And 25 is not going to be a problem to plug into this logarithm because you'd have 125 minus 4. That's fine. All right, so there. That's the exponentiating method. Let's look at a slightly more difficult version of it. And this is slightly more difficult because you got two logarithms on the same side of the equation, but that just means we do what we did a moment ago. We use our properties of logarithms in order to make a single logarithm on this side of the equation. All right, you should know how to do this. Use the quotient property, make this a single logarithm, and then exponentiate both sides. Notice that these are base 10 logarithms, so keep that in mind when you exponentiate both sides. Alright, so here's the left side of the equation written as a single logarithm. And next we're going to exponentiate, make both sides a power of 10. Right? And then the 10 and the log base 10 cancel. And then we need to employ the strategy where we get, no, that's not right. I'll have to change the right side of the equation here in a moment. Let me finish my thought though. We need to multiply both sides by x minus 7. Now when I say the right side of the equation is wrong, that should have been a 10 to the 0 power right here. And 10 to the 0 power is 1, it's not 10. So when we multiply both sides of the equation by x minus 7, we're just going to have 3x minus 5 equals x minus 7. So 2x equals negative 2. X equals negative 1. And let's make sure that works in the equation. If x is negative 1 and I plug in negative 1 in for x right here, I'll have negative 3 minus 5. That would make me have a negative logarithm. Well, the only solution we had doesn't work, so we're going to say there's no solutions here. Because that's as extraneous. Alright, last example. Try it out, see what you do. Oh, by the way, one hint. You want the two logarithmic expressions on the same side of the equation, and you want them each on the opposite side of the equation from the constant term that's there. So move this logarithm to the left side. Go. Alright, you got this so far, right? And then go ahead and make that into a single logarithm using the quotient rule. Now, time to exponentiate. Then you get x squared over 12 is equal to 64. That's what 4 to the third power is. Oh, some big numbers to multiply here. Let's multiply both sides by 12. Now, 64 times 12 means 64 times 10, which is 640, plus 64 times 2, which is 128. 640 plus 128 is 768. And then we'll take the positive and negative square root of both sides. Now I'm also going to simplify the radical, and I'll give you a quick hint as to how I'm going to do this so easily. Remember, you look for perfect square factors, don't you? Alright, well, 64 is a perfect square, isn't it? And within 12, you've got a 4 times a 3. Now I mentioned that because it was 12 times 64 that gave us 768. Well, if we could do 4 times 64, that'll end up being the perfect square factor. And 64 times 4 is 256, so that's the square root of 256 times the square root of 3. And the square root of 256 is 16. Now let's see if both of those solutions work out. The only logarithm that has a variable as part of its argument has an x squared, and whether we plug in a positive or negative value for x, that would be a positive. Each answer is in our domain. Those are our solutions. Thanks for watching. Good luck with these.